the second effect of general relativity. Here we go. Oh, I'm in the way. Mass bends time. Mass bends time. And you guys have been wanting to talk about time for a while now. But what does that mean? What does that mean? Okay. Oh, somebody's asking, what is being bent? Do you mean when I'm talking about mass bending time or when I'm talking about mass bending space? Because for mass bending space, what's being bent is the nothingness. It's the vacuum of space. For mass bending time, I mean time, the concept of time itself is being bent. Okay? The concept of time itself is being bent. Now, what do I mean by the concept of time bending space? Well, I'll go ahead and jump to the conclusion on this one. When time is bent, we can't picture what that means in our head, but its result is time slowing down. Bent time is slow time. So mass causes time to slow down. So wherever there is gravity, time is slow. That's the second effect of general relativity. So you can think of it as gravity slows time down, but really its mass creates both of those things. But yeah, so the more gravity something has, the slower time will be on that object. So let's do some examples. Because this is some crazy stuff. Okay. First up, why am I out of focus? Focus. There we go. Okay. Sorry about that. Okay, so here we go. Let's start up the document cam again. First question I have. Let's say that this is the Earth. And way up here is space. My first question is, where is time faster? On the Earth or way out in space? Where is time faster? Which one of these two would have faster time? Keep in mind, gravity slows time down. So which one of these two places would have faster time? Space. Because there's more gravity on Earth than way up in space, time will move faster in space than it does on Earth. You haven't known it, but your entire life you have been spending in slightly slowed down time. It's slow here. Time is a little slower here than it is naturally up in space. Is it a lot slower? Is time a lot slower for us on Earth than it is for astronauts out in the space station? Is it a lot slower here on Earth than it is up in the space station? No, it's not. Why? So why does Earth not slow time down very much? Why does Earth not slow time down very much? Well, remember, what slows time down? Gravity. So why doesn't Earth slow down time very much? See if you guys can figure that out. If it's gravity that slows time down, how come Earth doesn't slow time down very much? Remember what we said about the gravity of terrestrial planets. What's our gravity like? Does Earth have a very high gravity? Not very much gravity. Remember, we said that Earth has enough gravity to, kill a human being, but Earth and the other terrestrial planets are considered to have a very weak gravity. So our gravity is not strong enough to slow down time very much. But it does do it enough that we can measure it. So here's the question. Have we proved that Earth slows time down? Let me see if you guys know that. If you had to take a guess, have we proven this? Have we proven that Earth slows time down? Yes or no? Take a guess. Yes, we have. We have. Remember, this is the theory of relativity. We wouldn't be able to call it the theory of relativity without a lot of proof. And this is one of the things that we have, that it's actually pretty easy to prove. All you got to do is get two clocks and put one of the clocks, whoa, lost my pen. Put one of the clocks on the Earth and put the other clock in space. So what we've done is we have manufactured identical clocks, and we've synced them up, and we leave one of them on the Earth and we put one of them in space. And compared to the clock that's sitting on the Earth, the space clock runs fast. So when we bring it back down to Earth, they're no longer synced up. The one that goes up in space is always a slight fraction of a second ahead of the one down here on Earth. So it's only faster by a fraction of a second up here. It's only slower by a fraction of a second down here. But it's measurable. And in fact, a lot of times when we have to communicate with satellites, we have to account for this difference in time. Because don't overthink this, where are all the satellites? Where are all the satellites that we're communicating with? They're in space. Yeah. They're in space. And where are we? We're on the Earth. So here's a good example. On your phone, you probably have you've probably used GPS before. You probably have used GPS. And what is GPS supposed to do? It's supposed to tell you where you are, right? And how does it do that? It does it by your cell phone communicating with satellites in space to triangulate your position, and it's able to figure that out. Now, the thing is, though, in order for that signal to go to space and then come back, that takes some time, okay? And while that signal is going, the Earth is rotating. So by the time the signal goes up and comes back down, you're going to have moved. But that's okay, because the GPS knows that the Earth is rotating, so it's able to account for that. But here's the thing, though. That signal goes up to space and comes back down. And so the satellite has to know that time goes slower on the Earth than what it's seeing from space. Because if it did not know that, it would actually think that the Earth turned a different amount than it actually did. And ultimately, I know this is like a really complicated example, but ultimately what it means is if the space satellites weren't accounting for general relativity, then they would get your location wrong by miles, okay? Because of the spin of the Earth being the way it is. So every time you use GPS, you're using general relativity. We have built that into that system, okay? So you can do general relativity today. Just make your phone do it for you, okay?